Okay, so in this video, we're going to review statistically evaluating bivariate correlation. So using statistics, how do we evaluate bivariate correlations? Are they good? Do we evaluate them as a strong correlation? Is it a significant correlation? So we're going to go over some broader concepts. We're not going to go into it as much in as much detail as you did in 320. So keep that in mind. We're not actually going to be calculating the bivariate correlation for the exams. But for the lab, you will be doing some statistical analyses. But good news, none of that is by hand. But you should be able to evaluate these statistical numbers, coefficients, right? What does it mean when you have a 0.8, 0.3, negative 0.8 when you have a bivariate correlation? So let's go ahead and get started. I forgot to put that on full screen, but here we are. So let's go ahead and move on to the next slide. So in this slide, you see two scatter plots, right? You have those on the right, and they're both looking at height, but the other variable varies between the two scatter plots. On one, you have height at age 2. That's the top one, right? So let's look at the top one. Look at the y and x axis. On the y-axis, you have height at age 18 in both scatter plots, and then you have height at age 2, and this is all in centimeters, for the top scatter plot, right? So you see the association, the correlation between the two. And keep in mind, when you see a line like that, that's the line of best fit. But let's put that aside right now. Look at how tightly these dots are around that line of best fit. When you have that, that signifies, oh, this is a strong relationship, right? You have a strong relationship between a person's height at age 2 and their height at age 18. So we can't say one causes the other because we just don't have that design in this kind of study, right? We haven't satisfied all the requirements that as psychologists, statisticians, we need to satisfy for us to claim a causal relationship. But it would be kind of weird to claim, well, the height at age 18 caused the height at age 2. So keep that in mind. Also assess that part. Okay, but we have this data. There's a correlation between these two variables, right? Height at age 2, height at age 18. We've done the study with thousands of participants. We did a really good job at sampling, random sampling across the US. So now we have this relationship. We have, I don't know, this might be a 0.4, maybe less, but we know that there's a relationship between height at age 2 and height at age 18. And if we have one, height at age 2, we could do a pretty reasonable job of kind of estimating what height this person's going to be at age 18, right? So because we have such a strong correlation, we can kind of make that, not guess, but we can estimate where you should be around age 18. If you're below that, maybe there should be some concern. So think about that. Like when we're following kids and seeing how they're growing over time, we can use this information to kind of assess, are they growing? Are they where we would expect them to be given the information we have about them, given the existing information regarding the correlation between height at age 2 and how that progresses over time for the US population, right? We have those averages. So we can make a pretty good prediction where you'll be at height, where you'll be in terms of height at age 18 from height at age 2. Now, when you look at the bottom one, you have, again, height at age 18, right? But the other variable on the y-axis is mother's height. So in other words, having the mother's height, is there a relationship between mother's height and the child's height at age 18? There, of course, there is, right? Because of genetics, there's a relationship there. But notice that the relationship isn't as strong. So when I'm saying the relationship isn't as strong, right away you should be thinking about effect size. So the effect size is the strength of the relationship between the two variables. So keep that in mind, right? So the relationship, or the strength of the relationship between mother's height and the child's height at age 18, it's there, right? Because of genetics, we're gonna have a relationship, but the relationship between, or the effect size between height at age 2 of that child and their height at age 18 is much stronger, right? It's a much stronger effect size. So that's the way you can use these scatter plots in some situations where we've done studies across hundreds, thousands, maybe tens of thousands of people. We can use this data to make predictions. I'm not going to go into the causal part because you might be thinking, that sounds like causal. We still can't claim what's causing which, although in these examples, you might be in a stronger footing to claim it's causal just because it wouldn't make sense for height at age 18 to cause height at age 2. You can't go back in time. And it wouldn't make sense for the mother's height to be caused by the child they had, right? Yeah, so you do have some examples like that where they're kind of fuzzy, right? So you want to, in those kind of situations, you want to go back to the data and see how they collected the data, and do they satisfy the 3 requirements for causal claims in those situations. So now going back to effect size. Okay, effect size, again, the strength of the relationship between both quantitative, or the quantitative and categorical variable, right? That's what effect size is, the strength of the relationship between the two variables. And in this case, that bottom one looks kind of fuzzy. I think when I took that screenshot, it came out that way. But thinking of these examples, which one has the strongest effect size? Now, look at the bottom one. So put aside the scatter plot for a second. Look at the bottom one, where it has r equals 0.2 and r equals negative 0.8. You might automatically go into like, well, a positive number is bigger than a negative number. I'm not asking that. I'm asking which of these numbers indicates the strongest relationship between two variables. And when we're thinking about correlations and effect sizes, a negative number and a positive number, they're equal in terms of strength. We don't care if it's positive or negative when we're evaluating which one is stronger. We care about which one is the biggest number. And in this case, 0.8 is a stronger number than 0.2. So think about it this way. Which number is closer to 1 or negative 1? In this case, it would be negative 8. If you had, so these are 2 different correlation coefficients. If you had 2 and one was negative 8 and one was positive 8, and I asked you which one is stronger, they're equal. They're equally strong, just as you can see here in the scatter plots. One might indicate a positive correlation and one might indicate a negative correlation. So mostly I flip that bottom one. It kind of looks weird because the x and y axes are on the wrong side. Ignore that. The point is that even if they're positive, so a positive would look like the one on top. From bottom left to bottom right, it looks like it's diagonally going up. It's as strong as one that's going from top left to bottom right if they're the same number. So if that top one was 0.8 and the bottom one was negative 0.8, they're equally strong. If one was negative 0.9 and the other was positive 3, the negative 0.9 would be the stronger effect size. So keep that in mind. Ignore the negative, positive sign when determining strength. I kind of paused there because I was like, well, you don't want to ignore it completely, because if I'm asking you to explain it, give me the direction, you need to look at the negative or the positive to explain, okay, if it's negative, it looks like when if it's negative when partying goes up, grades go down, right? So it does help you explain. So you don't want to ignore it, but when you're evaluating which one's stronger, then you kind of can ignore whether it's positive or negative. Then you're just looking for the larger number. So usually larger effect sizes are more important. That's what we're looking for. So usually that's what we care about. That's the only thing we care about. Not only, but that's the thing we care about most in most situations, right? Because it tells us there's a strong relationship between our two of our variables. And here I have the table to remind you what a strong, medium, and weak relationship look like. But let me give you a situation. In one study, and it's in your textbook, they had 22,000 participants, right? They had 22,000 participants, and they had half take aspirin and half were in the control group, meaning they didn't have aspirin, they had some kind of placebo maybe, and they found that there's a 0.03 relationship between taking aspirin and reduced number of heart attacks. Okay, so in that situation, that's a super small effect size, right? But then I have to move my mic out of the way for a second. It resulted in the group that was taking the aspirin had 0.08%, right? Less heart attacks than the people who didn't take aspirin. Now, does that sound like a lot? No, right? 0.08%, it's not even 0.1%. But you know what? Let's try something out. Now, I'm going to take you to Google for a second. Google world population. So 7.8 billion. So let's see if this works. 7.8 billion times, so it was 0.08%, but to turn it into a decimal from a percent, you have to add 2 more zeros, right? Let's see if this works. Okay, cool, it worked. So that means if 0.08% had less heart attacks in the world population, all the world, that means 6,240,000 people would not have a heart attack if they took aspirin. So when we're dealing with the world population, that tiny effect size could help so many people, right? So that's kind of the example they're trying to make, right? That, well, yes, most of the times we care about the stronger effect size, but you have to take the situation into account. If we're dealing with lives, medical studies, and this many people benefited, you would stop the study before publishing and give those people that had the placebo aspirin because of just how many people this could save. So keep that in mind, that yes, generally we care about the large effect size, but you kind of have to take the context, the situation into account. You have to take into account the population of interest. What are the consequences and the benefits, right? So if the benefits are that we have this many people that have less heart attacks, this is awesome. This is great. We need to publish this. if the consequences are that 0.08% of the participants die based on this intervention, based on this new medication, then you need to stop right away, right? Even one person dying in the experiment is too much. Nobody should die, right? So the effect sizes, generally, rule of thumb, stronger effect sizes we care about the most. But you need to take into account who it's affecting, what it's affecting, what are we studying. Remember this specific example, right, as an example that shows how small effect sizes sometimes do matter. Okay, so now we're going to go over outliers. Here you have an example of an outlier. So this is from this slide I used for my 8 a.m. class I used to have. And yeah, if you like an 8 a.m. class, you're an outlier as a student, even as a faculty member. As a faculty member, a lot of faculty don't start their day until 10 a.m. Then we might stay up late till like 2 or 3 a.m., but we start late like most students. So you're an outlier if this is you. Okay. So one thing to consider is if one extreme score, so if a participant has an extreme score on one of your variables, is that changing the average or the relationship between the two variables overall and leading to misleading findings? So for example, here you have an outlier on example A. We have an R coefficient of 0.37, right? You have that one dot on the top right. And you can see that compared to the other participants on this scatter plot, they seem much higher. Then when you take them out, you see that what might be something between a medium and a strong relationship drops to a pretty clear strong relationship, or R coefficient of 0.26 once you take that participant out. So you have to ask yourself, are there any outliers, and how might they be affecting the overall effect size of my bivariate correlation? Here are two other examples of how outliers affect, well, actually no, this is the same example on the left. On the right, you have a new example. You see that one participant on the top right, take him out, and then you end up with the R coefficient of 0.19. You go from a strong effect size to a weak effect size. That's crazy, right? So just removing one participant had that influence on your overall effect size or your R coefficient. So keep that in mind. Think about it in terms of averages, right? If you have a group of friends, let's say a class. You have a class of 5 students. Everybody scores a C. So 70 points out of 100. Then you have one student out of these 5 students. So 4 get 70s, 1 gets 100. So this one student gets a perfect somehow. Then that brings the average up. Well, actually, let's look at that. Oh, there you go. So 70 plus 70 plus 70 plus 70 divided by 4. Actually, let me put parentheses over that. Gives me 70, right? But then, even if I had the 5th person, and let's say they scored a 75. I should divide by 5 now. So you have a 71 on average. But let me show you how that outlier. So we're not dealing with averages and bivariate correlations, but it's essentially the same idea. So look at how that outlier changes the average. And let's say we let's say one was a B. So I see this as a faculty member. I have this tiny class of 5 students. Like, oh, this is great. The average is 78. I don't have to curve anything because that's what I was hoping for, this average. But does this average represent how well the class did? Does this represent a good picture of how people did in the class? I would argue no. This especially high score brought that average up, right? Going back to the slides, this outlier on the right, where you have the R equals 0.49, brought this bivariate correlation coefficient way up, right? It made it look stronger than it actually was. Take them out, you have a weak relationship. That's the effect of an outlier. So when you're evaluating a bivariate correlation, this is something you have to look at. You kind of have to eyeball it first. You would do a scatter plot and kind of look at the individual numbers and see, does anybody really stand out compared to the other participants? What you want to avoid, though, is removing participants because they don't fit your hypothesis. Now, let's say you had 5 participants who scored very high, ended up going against what you hypothesized, and you're like, oh, well, I think those are outliers. So if that's guiding your decision, then you're introducing bias into your analysis, and that would get you in trouble. That would get you not published. That would get, if you got published and people found out you did that, they would retract the paper. So you're really looking at, well, is there 1 or 2 participants, a few participants? Now, a few means depends on how many participants you recruited, but are there a few participants that are outliers in your study? Now, the next part is assessing, well, is this a statistically significant bivariate correlation? Statistically speaking, do we have a significant relationship between the 2 variables we're measuring? Now, this could be a tricky concept. In your previous class, we've discussed it. You heard it, discussed it in terms of rejecting the null. Yes, it's related to that, but I'm going to simplify it and try to turn it into everyday language as much as possible. If you're going to go into statistics, if you're going to become the type of psychologist that focuses on statistical evaluation, then yes, make sure you know that. In grad school, you'll have time to review that a little bit more. But I want you to kind of have a general understanding of what this means. It's moving my mic a bit. Give me a second. Okay, might get louder. This p-value, right? So when you look at a statistical analysis, a correlation, a t-test, and ANOVA, we've told you your p-value should be below 0.05. And that's true. Now, what does that value of 0.05 mean? Right? Most of the time in class, I get responses like, well, it means that if you get a p-value below 0.05, it means your finding is statistically significant. You can reject the null. If it's above that, you can't reject the null. Okay, then what's that mean? Usually, this is where I find that most students get stuck. Most students don't really understand what that means. I'm a qualitative researcher, so it's taking me some time to understand what this means. And even now, I have to refresh my memory kind of to remind myself. So, so now we're back. I left off with what do p-values mean? Let's get back to it. We've used 0.05. What does this mean? So when you're saying that you had a p-value of less than 0.05, think of that as a percentage, 5%. We had a less than 5% probability, likelihood, chance that you found these findings when they actually don't exist. That you found a relationship between these two variables by mistake, right? And we want to get that chance of making this mistake as low as possible. As a field, psychology, sociology, the social sciences pretty much, that includes education, have chosen 5%. You might be asking, well, what do you mean chosen? Well, it could be lower. You could say, well, no, it should be less than 3%. But we've chosen this as our criteria, right? Now, if you go into medical fields, medical research, when people's lives are at stake, we want to minimize that chance that you found that this medicine is more effective than existing medicine, or that it's helping people's life. We want to reduce the probability that you found a relationship between taking that medicine and feeling better or reducing negative symptoms. So in medical fields, they actually use less than 0.01. They want a less than 1% chance that you found this relationship when it's actually not there, meaning that you found that this works when it actually doesn't work. So when you're dealing with people's lives, that makes more sense. In the social sciences, it's 5%. So, okay. So now going back to this, here you have an example. Just to bring it back to what we've been discussing before, we're looking at that sample, and we're looking at the relationship between engaging in this sport of motocross and the likelihood of getting injuries, right? And if we find a relationship, if we're able to get a p-value that's less than 0.05, meaning people who engage in this sport more are more likely to get in serious injuries, which would make sense, right? To get that finding. You want that to be below 0.05 because you want a less than 5% chance that you found this by accident. And you want to make sure that your sample reflects a population. So you did a good job of random sampling. So you can then generalize these findings to the population of interest. Now, in the blue, I actually have age, right? Okay, so let's say we found that younger motocross riders get into more accidents. So there seems to be some relationship between age and getting into accidents. Now, if I did a good job of sampling, if my p-value is less than 0.05, then I'm on good grounds to generalize these findings to the population of interest. If my p-value is 0.1, that means there's a 10% chance that I found these findings when they actually don't exist in the sample or population of interest, right? So keep that in mind. We are not willing as psychologists to accept anything above a 5% chance that you found a relationship between these two variables when this relationship actually doesn't exist in real life. So let me say that again. As psychologists, we're not willing to accept anything above 5% error regarding finding a relationship between the two variables you're studying when there might not be a relationship. But yes, that means that there's a 5% chance that person who published their finding might have found a relationship when there actually isn't a relationship. But that's why we also have replication. Okay, maybe that study found that, but the next researcher should replicate that study, and do they find the same thing? Great. In other words, what are the chances that you found that correlation when it really does not exist? right? That's pretty much what the p-value tells us. So I'm going to end here. If you have questions, again, as always, please reach out. Dr. R, signing off. Now, if I could only reach my keyboard to turn this off. Okay.